in this lecture, which will be answering these questions: what is the cardinality of infinite sets? Are all infinite sets equivalent? Which has more elements, the natural numbers or real numbers? And can a set be equivalent to its subset? When we were small kids, the first thing we learned maybe were alphabets, but after that we were taught how to count. 1, 2, 3, 4, 5, and we can go on and on counting. Have you ever wondered how many natural numbers there are? These numbers are called natural numbers or counting numbers because they develop naturally and they're used to count. But first, let us define the cardinality of a set. We say that the cardinality of a set is just the number n such that A, the set A, for example, has 5 elements. So, as an example, the set of vowels A, E, I, O, U has cardinality 5 since it has 5 elements. Now, for a finite sets are easier to handle. Take note that if A is a finite set, n of A is equal to k if A can be placed in a one-to-one correspondence with the set 1, 2, 3 up to k. So, a one-to-one correspondence is simply a function. It's a correspondence between two sets A and B such that for every x in A, there exists exactly one element in B mapped to it, and for every b in B, there corresponds exactly one element in A. So, for example, for the set A, E, I, O, U, its cardinality is 5, and we can place the set A, E, I, O, U in a one-to-one correspondence with the numbers 1, 2, 3, 4, 5. It can also be with 5, 4, 3, 2, 1. This correspondence need not be unique. So it's just a pairing off. Like in real life, we want everyone to have a partner. Bawat isang tao, isang partner lang. Hindi pwedeng 2:1 or 1:2, isang tao, dalawa ang kanyang partner. Hindi yun fair, di ba? So we want it to be a one-to-one pairing. Now, we define two sets to be equivalent if they have the same cardinality. So equivalently, A and B are equivalent if they can be placed in a one-to-one correspondence. So for example, the set A equal to A, E, I, O, U and the set B with elements 1, 2, 3, 4, 5 are equivalent. So take note also that if A is finite and B is a proper subset, meaning there are elements of A which are not in B, then the number of elements in B is strictly less than the number of elements in A. So for example, if A is 1, 2, 3, 4, 5 and B is the set 2, 4, then take note that the cardinality of B is 2 and the cardinality of A is 5. So the cardinality of B is strictly less than the cardinality of A. Now the question now is this also true for infinite sets? In particular, can an infinite set possibly be equivalent to a proper subset? So maybe this is difficult to imagine, but we can see later that this is true. So let us first look at the familiar number set, the set of natural or counting numbers. So n is the set 1, 2, 3, 4, 5. The kth element is k, and then the next element is k plus 1. This is an infinite set since it goes on and on. What is the cardinality of this set? When we have a finite set, we can easily count. But if we have an infinite set, can we define the number of elements? Of course we can. We just have to assign a certain symbol. So what is the cardinality of the set of natural numbers? We call it the Aleph null, which is represented by the Hebrew alphabet Aleph. It's also called Aleph naught or Aleph 0. Let us now answer the following question. So you've always heard that infinity plus 1 is still infinity. What is infinity times infinity? Now this is something not so well defined, but if we have Aleph null, what is Aleph null plus 1? What is Aleph null plus 2? What is Aleph null plus Aleph null? And what is Aleph null times Aleph null? So maybe this is a bit too complex, but I can easily show that all of these will be equal to Aleph null. Now, David Hilbert is a German mathematician and one of the most influential mathematicians. He gave the paradox of the Grand Hotel or the Hilbert Hotel problem, which presented counterintuitive properties of infinite sets. So I am warning you, this is counterintuitive, so it's not the usual thing. That's not the usual way of counting. So this is the Hilbert Hotel problem. Imagine a hotel with infinitely many rooms, which can only accommodate one person per room. So, and for a certain night, each room is occupied. So, if a new guest arrives, can he be accommodated? Kasya pa ba siya? What if two guests arrive? Kasya pa ba sila? What if infinitely many guests arrive? Kakasya pa ba sila? So take note that let's number the rooms as room 1, room 2, room 3, and remember there are aleph null rooms, so this will be infinitely many. Each room is occupied. Let's call them guest 1, guest 2, guest 3, and so on. So suppose that one person arrives and he wants a room, he needs a room. So can he still be accommodated? So anong gagawin ng hotel manager? Remember that all the rooms are already occupied by one person. Two persons cannot share a room. So dapat 1:1 lang. And there are aleph null guests, there are aleph null rooms. So can he still be accommodated? So what do we do? Assuming that all the guests are nice, you can request them to transfer to the next room. That's what you will do. Ask guest 1 to go to room 2, ask you guest 2 to go to room 3, and so on. In other words, guest N, who is in room N, will now go to room N plus 1. Take note that you have infinitely many rooms, so every room has a room beside it. So everyone can move one room, let's say to the left, for example, and that will vacate room number 1, meaning the guest who arrived can still be accommodated. So what will that mean? The number of rooms is aleph null. The number of guests is aleph null plus 1 with the arrival of one guest. But there is still a one-to-one correspondence between guests and rooms. So what will that mean? Aleph null plus 1 is still equal to aleph null. So adding 1 does not change the value of aleph null. Now, what if two guests arrive? Can they still be accommodated? So similar to our solution for one guest arriving, we simply move guest 1 to, can you guess? Guest 1 will move to room 3, guest 2 will move to room 4, guest 3 to room 5, and in general, guest N will move to room N plus 2. So if you're occupying room 10, you're just going to move to room 12. If you're occupying room 1 million, you just go to room 1 million 2. And you have infinitely many rooms, aleph null number of rooms. But with this movement, the first two rooms will now be vacated. So therefore, the two new guests will be accommodated. So what does this mean? Aleph null plus 2 is still going to be equal to aleph null. So in general, suppose k number of guests arrive. K can be any number. They can still be accommodated by transferring guest 1 to room k plus 1. So example, if there will be 10 guests arriving, you ask guest 1 to move to room 11. You ask guest 2 to move to room 12, and so on. In general, if k guests arrive, you simply ask the guest in room number k, room number n, to move to room k plus n. So what does this mean? This will mean that aleph null plus k is equal to aleph null. So it does not really change the value of this of aleph null. Now imagine we have a Hilbert hotel with infinitely many rooms, and suppose Hilbert has a bus. So let's call it the Hilbert bus with infinitely many seats. And suppose the Hilbert bus arrives and all the seats are occupied. So what does this mean? It means that the Hilbert bus has aleph null passengers. So suppose they come from somewhere and they want to be accommodated for the night, kakasya pa ba ang mga nasa Hilbert bus? If yes, this will actually mean aleph null plus aleph null is still going to be aleph null. Kaya pa ba? Kaya pa yan. So how do we do it? So what we do now, it's not that simple. What we do is you ask the person, guest 1, in room 1 to move to room 2. You ask guest 2, who is in room 2, to move to room 4. Guest 3, where do you think should he go? The guest in room 3 will now go to room 6. In general, the guest in room n will go to room 2 times n. And if n is any natural number, 2n is still going to be a natural number. Therefore, all the guests can move to room 2 times n. So what does that mean? We have occupied only the even numbered rooms. And if you think of all the even numbers, this will still be infinite. So what will be vacated will be the odd number rooms, room number 1, room number 3, room number 5, and so on. So therefore, you still have infinitely many rooms vacated. And these are now ready for occupancy, so the passengers in the Hilbert bus can now be accommodated. So what does that mean? It means that aleph null plus aleph null is aleph null. So far, is that clear? So let us review. We have said that aleph null plus 1, that's the one guest arriving, is still aleph null. Aleph null plus 2 is still aleph null. Aleph null plus k is still aleph null. And now, aleph null plus aleph null is still aleph null. Meaning 2 times aleph null is aleph null. And you can also show somehow that aleph null plus aleph null plus aleph null is still aleph null. So what you can do is you vacate all the rooms. So babagin lang siyang only you just leave all the multiples of 3 rooms vacant, in which case infinitely many can still fit in. Now, before we deal with the question, what is aleph null times aleph null? Pwede pa ba yun? Let us now consider the number sets defined by n, the set of natural numbers, w, the set of whole numbers, which will start from 0, and then 1, 2, 3, 4. E is the set of even numbers, that will be 0, 2, 4, 6, 8. The kth element being 2 times k. So these are the natural numbers or the whole numbers, which when divided by 2 will leave no remainder. And 0 is an even number. And O is a set of odd numbers, 1, 3, 5, 7. The kth element is 2k plus 1. In other words, odd numbers are just even numbers plus 1. And you have Z, the set of all integers. These are the whole numbers together with the negative of the natural numbers. And Q is a set of rational numbers. So they are called rational because we can imagine them. These are just numbers of the form A over B, where A and B are integers. B is not 0. And in terms of decimals, these are just the terminating or non-terminating but repeating decimals. Example, 3/4 is a rational number, 1/4, 1/3. 1/3 is non-terminating but repeating. 1/4 is a terminating decimal, that's 0.25. Now, but we also have the so-called irrational numbers, and these are numbers which are not rational, meaning we don't use them in our everyday lives. Example will be pi, square root of 2, and these are, in terms of decimals, the decimals which are non-terminating and non-repeating. So the set of real numbers is just the set of rational union the set of irrational numbers. So if we represent this using a Venn diagram, you see that these are 2 disjoint sets, rational, irrational. Inside rational will be the natural numbers, inside the set of whole numbers, inside the set of integers. And take note that the set N is a proper subset of W, the set W is a proper subset of Z, and Z is a proper subset of the rational numbers, because there are rational numbers which are not integers, there are integers which are not whole numbers, and 0 is a whole number but it's not a natural number. So, ang tanong, what is the cardinality of these sets? So what is the cardinality of W, of Z, of even numbers, of rational and irrational numbers, and the real numbers? So for example, the set of natural numbers is contained inside the set of whole numbers, but you can establish a one-to-one correspondence. To show that a certain set has cardinality aleph null, you simply have to show that you can pair off one set with a set of natural numbers, which is one-to-one. Meaning, isang bawat natural number ay may kapartner doon sa isang set and vice versa. So if you look at the set of natural numbers 1, 2, 3, n, and you look at the whole numbers 0, 1, 2, you just pair off 1 with 0, 2 with 1, 3 with 2, in general, n with n minus 1. So in other words, there is a one-to-one correspondence. So kahit mas maliit tignan yung natural numbers than whole numbers, actually they have the same number of elements. This is counterintuitive. Unlike in finite sets, if it is a proper subset, it always has less elements. But for infinite sets, it's a different thing. Now, let's look at the set of even numbers, 2, 4, 6, 8, and so on. We can include 0. And then the odd numbers be 1, 3, 5, 2n minus 1. You can easily have a pairing. Let's say 1, the natural, will go to 2, even. 2, natural, will go to 4. 3 will go to 6. N will go to 2n. So if I give you, let's say, 10 as a natural number, it will be paired off with 20. And let's say I'll give you an even number, 100. What is the natural number which goes with it? It will be 50. So take this well defined, because if n is natural, 2n is even. And if m is even, you divide it by 2, it's still going to be a natural number. So what does it mean? Even numbers, this will be a proper subset of the natural numbers, but they have the same number of elements. So parang nakakashock, but it's true because we have shown that there is a one-to-one correspondence between natural and even numbers. For the odd numbers, it can also be similar. So even if parang kalahati lang yung even ng natural, they have the same number of elements, meaning 1/2 of aleph null will still be aleph null, the same manner that twice aleph null is still going to be aleph null. How about for natural numbers and integers? Take note, natural numbers parang kalahati lang siya ng integers, and we can use the same reasoning. Pag kalahati lang or times 2 siya ng isa, and 1 is aleph null, the resulting set is still going to have cardinality aleph null. So the one-to-one correspondence will be, if you have, let's say, the number 0, so integers, we can pair it off with 0. Then what you do now, you cannot pair off 1 with 1, 2 with 2. What will happen? If you have this pairing of positive integers with natural numbers, there will be no more partners for the negative integers. So you have to make sure lahat may kapartner para lahat masaya. So what you do is, you divide z into 2 parts or n into 2 parts, which will be even and odd. And now you have to map the natural numbers which are even with the positive integers, and the natural numbers which are odd with the negative integers. And this will ensure that all of them will be paired off with one element. So therefore, this will be a one-to-one correspondence, and this will mean that the set of natural numbers and the set of integers are again equivalent. Again, the set of integers is seemingly bigger than the set of natural numbers because you have negative of the natural numbers, but eventually they have the same cardinality. Now, it's a little bit more tricky for rational numbers. What you do is you can just represent the rational numbers as an array. So you have the numbers 1, and then 2, and then 3, then form all possible combinations. So you can have the first row will simply be 1 over 1, 1 over 2, 1 over 3, and so on. The first column is 1 over 1, 2 over 1, 3 over 1, and so on. So you will have aleph null rows and aleph null columns. So you will have how many elements all in all? It will be aleph null times aleph null. So what is aleph null times aleph null? If we can show that there is a one-to-one correspondence between the rational numbers which we have formed this way, and these are only the positive rational numbers, then it will mean that rationals and natural numbers are actually equivalent. Now, you cannot make the pairing 1 goes to 1 over 1, 2 goes to 1 over 2, because for the first row, your natural numbers will all be used up. The same manner, you cannot just use the pairing with the column. So what you do is, the trick is, you imagine an infinite string, and then number that with 1, 2, 3, 4, the natural numbers, and you string the rational numbers diagonally. So if you do it this way, take note that 1 over 1 will be mapped to 1, 1 over 2 will be mapped to 2, 2 over 1 is mapped to 3, and in general, n over m is mapped to, it's something not simple, n plus the quantity m plus n minus 1 times m plus n minus 2 over 2. A bit complicated, but it works. And this is a one-to-one correspondence. So what does it mean? Aleph null times aleph null is still aleph null. So let us recall again, review. The even numbers and the odd numbers are proper subset of n. N is a proper subset of W, Z, Q, but all of these sets have the same cardinality, aleph null. Hence, they are all equivalent. So this is only a property of infinite sets. An infinite set may be equivalent to a proper subset. And this is not true for finite sets. In fact, you can define infinite sets to be infinite. A set is infinite if it can be placed in a one-to-one correspondence with a proper subset of itself. So we say that A is countably infinite if it is equivalent to the set of natural numbers, meaning aleph null. So theoretically, it's still countable because the numbers are discrete. So you can count 1, 2, 3, and so on until you die, but you can continue counting and counting. It will never end, but you can count, okay? So, but is the set of real numbers also countably infinite? Meaning, does it have a cardinality equal to aleph null? So, anong mas marami? Real numbers or natural numbers? So, this time, maybe you can say that real numbers, but it took some time to prove that. Okay, so it's intuitive, mas marami ang real. But remember, earlier, you thought that natural numbers have more elements than even numbers. So there was a German mathematician, George Cantor, who developed set theory. He studied infinite sets and their cardinality and showed that there are more real numbers than natural numbers. Specifically, he showed that the cardinality of n, the set of natural numbers, is less than the cardinality of the set S, which is the open interval from 0 to 1, meaning the set of all real numbers between 0 and 1. Take note, if a number is between 0 and 1, it can be expressed as a decimal of the form 0 point, then you have numbers following 0 point something. And this can be terminating, it can be non-terminating. For example, 0.25 is between 0 and 1. 0.333 ... is also between 0 and 1. So Cantor used what we call now the diagonal argument to show that we cannot establish a one-to-one correspondence between n and the set S. And the argument is by contradiction, so we call it now the diagonal argument. So what do you mean by argument by contradiction? So he first assumed that n and S will have the same number of elements. What do you mean by a set has aleph null elements? It will mean that you can theoretically enumerate all. So suppose you can enumerate all elements between 0 and 1. So take note that in this argument, if you list down a number, let's say R1 is 0.00012345, let's just keep it finite first. R2 is 0.04256437. R3 and R4 are given by 0.2957836 and 0.526790113. We take note that we can actually create a new number from these four. which will be distinct from the 4 numbers enumerated. So we take note in R1, the first decimal digit is 0. In R2, the second decimal digit is 4. In R3, it's 5. And in R4, the fourth is 7. How do we form a new number which is not the same as the previous 4 numbers? What we do is we simply choose the decimals. The first decimal should not be equal to the first decimal of R1. The second digit should not be the same as the second digit of R2. The third digit is not equal to the third digit of R3. So for example, the first decimal is 0. Just choose any number not equal to 0, for example, 3. The second decimal of R2 is 4. For the second decimal of the new number, choose anything not equal to 4, for example, 1. So if we proceed this way, take note, we form the new decimal 0.3148, and it's not the same as R1, R2, R3, and R4. So if we extend this argument for all the decimals between 0 and 1, we actually can show that you cannot enumerate all the numbers between 0 and 1. So this is how Cantor did it. You have the set, the number 1 is mapped to R1. For example, you can enumerate all real numbers between 0 and 1. So 1 is mapped to, let's say, R1 of the form 0. We express the decimals in the form A11, A12, A13, and so on. 2 is mapped to R2, 3 is mapped to R3. In general, n is mapped to Rn, and Rn is expressed as 0.a and 1, that's just one number, a and 2, a and 3, and so on. And then we now show that you cannot enumerate all because you can actually create another number which is not in the list. So we are assuming that all the numbers between 0 and 1 are already in this list. So how do we create that number? So let R be the number, let's say 0.B1, B2, B3, and so on, that can go forever, where B1 is not the same as the first digit of R1, B2 is not the same as A22, which is the second digit in R2, and Bj in general will not be the same as the jth digit of Rj. And take note, because this number is not equal to R1, R2, R3, because they differ by at least one numeral, it cannot be equal to any of the given numbers, R1, Rn, and so on. So what does that mean? The set of natural numbers is not equivalent to the set of points between 0 and 1. The set 0 and 1 is just a subset. It's a small part of the set of real numbers, but it has a lot more elements than the set of natural numbers. So we cannot place the two sets in a one-to-one correspondence, so which means that the cardinality of the set of natural numbers is strictly less than the cardinality of the set of points between 0 and 1. Question is, which has more elements, the set of numbers between 0 and 1 or the whole real numbers, the whole set of real numbers? Take note, the set 0, 1 can be expressed as a finite line segment, and the set of real numbers can be expressed or can be represented by an infinite number line. You are familiar with the number line. So 0, 1 is finite, R is infinite. Can we place them in a one-to-one correspondence? So let's do it geometrically. So for example, if you have two finite line segments, you can place them in a one-to-one correspondence by just get any point outside the two lines and then connect that point to one point on one given line, and then just connect this point and extend so that it intersects the second line, and this will be the partner points. So if you continue this way, all the points in the first line will be partnered with another point in the second line. So there's no problem if you have finite lines. But you must also do the partnering in the correct manner. If you just draw perpendicular lines, it will not be a one-to-one correspondence because some points in the longer line will not be mapped to points in the shorter line. Now, how about if you have an infinite line and a finite line? So what we do is you simply bend the finite line, and you can now map it this way, get the midpoint of that arc, and you simply map the points with a fixed point, and then pair it up with the points on the curved line, and then try to see where it intersects the line on the number line. Now, this can be easily seen if you remember the tangent graph. You have the line pi over 2 or negative pi over 2 to pi over 2 is mapped actually to an infinite line. Meaning, if you have tangent x and you simply let x be between negative pi over 2 and pi over 2, then it will generate the whole set of real numbers. This is just a one-to-one correspondence. 1 point between negative pi over 2 pi over 2 to 1 point between negative infinity to positive infinity. So there is a one-to-one correspondence between a line segment, which is finite, and an infinite line. Again, counterintuitive, kasi mukhang mas maraming points ang infinite line, but actually they have the same number of points, and it's not Aleph null. This number is greater than Aleph null. Now, Cantor went into depression several times in his life, and they noticed that each time he was depressed, he would be thinking about one question. Is there a number between the cardinality of the set of natural numbers, Aleph null, and the cardinality of the real numbers, which we call now Aleph 1? So up to the day that he died, and he died in a hospital, I think thinking about this problem, it was that he never was able to prove it, that there's a number between Aleph null and Aleph 1. But he was able to establish that there are different degrees of infinity. Aleph null is the smallest infinity. It's the cardinality of natural numbers, and the set of real numbers will have a bigger cardinality, which we now call Aleph 1. Now, Cantor's big question is now called the continuum hypothesis, which states that there is no set whose cardinality is strictly between that of the natural numbers and the real numbers. It seems to be a very simple question, but it was included in the 23 problems posted by Hilbert in 1900, and this was the first problem. These were important math problems during that time which were unsolved. Some have been solved, but for the continuum hypothesis, I cannot say that it has really been solved. Well, it has been shown that at this point, you cannot prove nor disprove it. So it seems that Cantor's thinking over it was not really in vain. It is a difficult problem, and it is difficult to prove it with the existing Zermelo-Frankel set theory, with or without what we call the axiom of choice. Perhaps if we change this set theory or the axiom of choice, maybe we can prove or disprove. So again, the things that we learned now are counterintuitive, but we learned something that in mathematics, we actually have to be open-minded, because what seems to be obvious is not maybe that obvious, and what seems to be real may actually be not real. But we can always show it, and we can prove or disprove our hypothesis. But if on a certain night you need a hotel, remember that there's always a room in Hilbert's Hotel. Thank you.